Hey everyone, so the technical difficulties are resolved. We're ready to stream now. So we're going to start off the afternoon session. It's going to be a mix of both production use cases again and a little bit of research at the very end of the session. So here's Jason from OctoML to tell you a little bit about what we're doing at the company, and off you go.
Thanks, Jared. And thanks, everybody. So I want to start with just a brief recap on who we are, deployment pain, and talk about our vision, and then talk about the Octomizer and TVM for everyone. So OctoML is a company we started about 5 months ago for making simple, secure, and efficient deployment of machine learning models everywhere. Also driving TVM adoption, increasing core infrastructure improvements and help funding those along with all of you folks here. And expanding the set of users who can deploy machine learning models by making services and automations and integrations. And so I'm going to touch on the first one of those today. So this is us, as you saw this morning. We're about 10 or 11 now, depending on how you count. And lots of us are here. And so, like I mentioned this morning, what are the deployment pains and complexities that people hit today? There's model ingestion and conversion. There's half a dozen to a dozen conversion scripts from Onyx to PyTorch and PyTorch to TensorFlow and TensorRT, and just and there's always a mixture of compatibility and offset coverage, et cetera. There's the kind of performance estimation and comparison across the Cartesian product of which models solve my pain points or topologies that I want to pick from, which frameworks that support the platforms I'm running, and then the hardware variants that I might have available to me for any use case. And then if you're using CodeGen, there's a raft of options, sometimes confusing. And then you need to sometimes do size reductions for deployment on certain class of devices. And then quantization, pruning, and distillation each have their own literature devoted to them that you might have to go and try to implement yourself or find some set of packages that do some of that. Then there's, if you're doing a non-custom or non-standard workload, you might have some custom operators either on the input or output side of things. And so then you need to figure out writing schedules and worrying about which hardware I need to support and do I implement this tensorization. Then there's lack of portability in terms of what package do I have and what can it run on at the end of the day. And then now that I have my model, I need to integrate it with some existing business application and monitoring system. And I need to go and package this and figure out the Android APK packaging story, or look into Debian packaging for the nth time because you can never remember how to do it right, et cetera, et cetera. So, and again, deep learning should be easy, right? Because it's just examples in, examples out, data in, data out. Like we've done this for decades, right? With traditional software engineering. And so why is it so hard with machine learning? And again, TVM is core to making that happen, but it's only the first step. We looked at this problem space. We kind of looked at the entire machine learning lifecycle, and there's a lot of activity happening on making training easier and machine learning platforms to do that. But in the optimization and deployment side, there's not as much tooling there, and it's still really painful. And there's a lot of pain here, like because the fan out is higher to the amount of places that you want to deploy and the number and type of environments that you want to deploy to. So that's the focus, and the idea is to reduce the amount of humans needed in the loop to make it possible for a data scientist to take a trained model and take it to production. So today I want to announce the Octomizer, which is our deep learning optimization as a service product offering. And essentially, TensorFlow or PyTorch or Onyx or other serialized models come in the front to a Python API and a web UI and more to come. And then we have a hosted service that can then allow you to generate optimized models for deployment on cloud and edge and mobile. And so let's dig into that a little bit. And I just want to give you, it wouldn't be any fun if we didn't try a live demo. So let's dive in here. Let's say I'm a data scientist and I've trained my model, and in lieu of a trained model, I'm just going to work with this tiny relay function here, just a single com2D layer. And I'm going to get back to this, but to demonstrate kind of the utility and flexibility of the Octomizer, I'm going to actually run the entire service locally deployed on a Kubernetes cluster on my laptop because oftentimes you don't want to trust just the cloud-hosted version of something. You want to run the entire infrastructure in your private cloud or on-prem. So in this case, I'm doing it on my laptop. And so there's a set of services running on the Kubernetes cluster that I'll get to later on my laptop. Plus, I didn't trust the Wi-Fi. And so I've got my tiny workload here. I have this Octomizer package that I pip installed from pip. And it's not quite up today, but once we open this up to public beta, you can do so. And then I get a private access token. And that's it. I'm off to the races. And I've already done those two things here. And so now I just need to use the Octomizer library here to upload my model. And I can give it a name and send a whole bunch of labels and parameters, et cetera, that I can use for selection that I'll get to later. And then if you want, you can just, that can be it. And you can just go ahead and download a package. And right now we support only Python, but this can then give you kind of various flavors of packaging, like a raw shared library with a C shim, or a Rust crate, or a Maven artifact, or a Android APK, et cetera. But that's not enough for us. We want to actually go ahead and run AutoTVM, so I can, on this model, run an AutoTVM job and pass it a bunch of parameters. Here, I'm just kind of restricting it to a shorter runtime so that we can get through the demo today. And then I can busy loop here and then download the optimized package. So just to, this is designed to show you kind of how approachable this is designed to be. Like, this is stuff that you could imagine showing the developer who doesn't know how to implement custom block sparse operations in TVM, for example. And so if we actually run this, against our, let's see, Python optimize, then you see that it uploads. It downloads the packaged version here. Right now, this is a Python package. You can also select a wheel if you want. And then it submits the AutoTVM job, and then runs AutoTVM in a separate Kubernetes job. And then in a few seconds, since I've tuned it down to a very short AutoTVM job, it'll return and give me the package back. And then I've got two packages here. And then now these are pip installable packages, so I can just install the package. And then once that installs, then I can show you whatever application I have. In this case, it's just a Flask application that basically, it's not even a cat classifier, but it's generating random data and then showing that to the user in raw string form, and then running that through the relay packed function, and then showing the output. And so we can run this, my application, and then click on the link here, and then voila, we're running relay with just a few steps. So that's just designed to kind of give you a flavor of how easy this is designed to be usable. And the idea is that over time we'll be adding more and more capabilities. We already have the ability to specify what GCP instance type you want to use and the number of threads if you want just a single-threaded worker. Being able to build and run against a specific TVM hash that's available in the open source TVM project, et cetera. And so what we do support today is auto-tuning of whatever library you want across both Onyx models and Relay models. TF Lite is coming as well as others. And then we support GCP Cloud instances, ARM A and M class devices. And this involves us running our on-prem fleet of several racks of Raspberry Pis and ARM microcontrollers. And then on the roadmap is additional cloud instances, more automatic quantization, hardware aware and performance aware, network architecture search, and compression and distillation, all in the sense of extending the class of models that are supported on more and more constrained hardware, so that you don't have to worry as much about will this model fit, because we can know ahead of time what target you're trying to support. And then so the other half of the demo here is, and I'm going to not go with the video because I'm dangerous like that. So here I can, there's actually the hosted version here, but I'll just do the local version. And so you can, if you want, you can upload your own model here, and then choose a file, and then upload it, and then it shows up here. And then if we want, we can kick off a benchmarking job on AutoTVM, and it shows up here, and then that'll be job status updated over time. And then soon to come is when you can click a button and then go and look at the performance comparison of your model across a suite of common models. So here it's a little hard to see, I guess, from the font size. But here we have SqueezeNet, ResNet, NLP models, BERT, etc. Today across TVM and Onyx runtime. You can compare speedups of what TVM performance is over Onyx runtime. So here we're doing better than Onyx runtime CPU across most models. You can, let's see, let's go back here. You can filter down to just TVM and then look at performance of relay optimization 2 versus 3, do a similar comparison. You can pick out a few models and look at their performance. And most importantly is you can click on an individual model and then look at performance breakdown per layer. Here the color is the runtime of each layer. So you can see that there's a couple of heavy layers at the beginning that we might want to look at. Perhaps changing our architecture and or just getting a better sense of what the performance cost of these layers are. And all this can be downloaded in raw form and visualized and played to your heart's content locally. You have all the details of what target settings and what instance and CPU, etc. So that's just the first stages of the demo and product that we have today. Oops, let me jump back to presentation. And so getting back to the deployment pain and complexity, you can see how we're already helping on the model ingestion conversion because all that's done on our side, and we ensure that we have as broad a coverage as possible by improving the TVM open source conversion and then using that in-house. Performance estimation comparison, just giving really easy way for users to kind of do these comparisons and drill downs. Optimization, we have a lot of things that are in works here, but I can't share any today. Same with custom operators in terms of shipping your model with custom operators and then getting those through the whole process. And then lack of portability. We have some of those pieces here today, and also with model integration. But you can see the kind of the direction we're headed here. And under the hood, like I mentioned, the entire stack is designed for easy cross-cloud and private cloud on-prem deployment. It's essentially a set of Kubernetes services and deployments using Kustomize for nice, easy, declarative, customizable deployments on Kubernetes. Using Rust and Actix Web for nice, lightweight, binary dependencies, self-contained. And our only external service dependency right now is an object store service, but that's quite easily changeable in the future if customers would like. And we support TVM and use TVM RPC trackers for connecting cloud devices to on-prem devices if you so choose, like we're doing on our ARM Cortex-M and ARM Cortex-A, ARM A-class devices. And like I mentioned, the GCP cloud instances and ARM and AMM class, and more to come. And so, just one more kind of view of what we're looking at is, today we want to focus on existing users with existing hardware, getting their machine learning models and requirements into production securely and efficiently. But in the future, the idea is to also, because execution and compilation for existing hardware and future hardware are not so different, we want to also give a route to users having a better sense of what their models would run on future hardware because, having come from a hardware company, I worked at Intel for quite some time, it was more difficult than necessary dealing with customers who often wouldn't want to share their models and then we had simulators that we couldn't share or weren't in a state to share. And so making that process easier for both parties is something that we would really like to accomplish. And so that's it for the kind of short sneak peek. So stay tuned through Twitter or email or our website. Reach out to me if you think this is something interesting to you or your customers. And because we're looking for beta partners to really nail kind of those real pain points. Because we have the rough structure here of solving a lot of pain, but we really want to work end to end on real use cases. And like everyone else, we're hiring. So come talk to us or see our website for more. Thanks. Any questions? Must have done a great job then.
All right, cool.
Cool. I'll take this.
Oh, yeah, this is yours.
Yeah.
Are we using yours, Luis? Yeah. All right, cool. I think.
Who's the next one?
I think Krzysztof is our next speaker.
All right.
Where is he?
So just ask him.
Krzysztof, are you here? Oh, there you are.
All right, up next, we're going to hear some more about TVM at Qualcomm. I'm looking forward to hearing about what you guys are up to. Here we go.
All right, thank you. My name is Krzysztof Parzyszek, and I work at Qualcomm Innovation Center in Austin. And today I'll talk about what we do, what our goals are with TVM, what we do with it, what we've done so far in terms of the work that we've done for TVM. I'll talk a little bit about the challenges that we've met, and then I'll finish with some discussion of the plans for the future.
Okay, so you can also use this big button.
Okay. All right, so our goals are centered around Hexagon. As you've heard about Hexagon today, it's a low-power processor, often comes with a vector engine called HVX. Both the core Hexagon and the HVX have very rich ISAs. They are well-suited for numeric integer calculations, particularly strong in int8. So that positions them very well for executing machine learning workloads. And so the first goal that we have is to add support for Hexagon to TVM. And like I said, to exploit the richness of the ISA. So there is a price to pay for how rich the ISAs are. And so the price is that when you want to write code by hand in assembly, you have to know what you're doing. It's not very easy to do, and you need to have a fairly high level of expertise to actually exploit the functionality that Hexagon and HVX provide. And also, it's a challenge for C and C++ compilers to generate those complex instructions, and the reason is that compilers, like for example LLVM, they break down the code into a fairly low-level LLVM IR, and then if you want to analyze the LLVM IR at the beginning, you can have a very complex analysis that tries to find opportunities to generate particular instructions, like VRMPY, for example, that was already mentioned in one of the previous presentations. But then you have to do that for pretty much each instruction that requires such an analysis. If you want to delay this until the instruction selection process, then what you're doing is you're looking for opportunities to find a particular complex computation in this broken down algorithm that TVM or that LLVM had already optimized. Both of these things are very difficult and it's and very challenging, and it's difficult to find to develop a robust solution to do it in a C and C++ compiler. And in a platform like TVM, where you have a very broad view, very high-level view of the code, The hope is that we can, instead of trying to analyze a very low-level IR, we can focus on the analysis of the algorithm and then pick the right implementation for it. Finally, we want to give TVM to our customers. We want to make it easy for our customers to use Hexagon and to exploit all of its potential. We already have a precedent with the domain-specific language, namely Halide. That's the language for image processing. We have given this to our customers, and we've had good success stories with it. So that leads us to believe that another DSL for machine learning will also be well received. What we do with TVM right now at Qualcomm is that we are treating it as a compiler for ops. So we already heard about this. We have other frameworks, other machine learning environments that we support, namely Hexagon and N. And we want to give the ability to our customers to develop ops for Hexagon and N. Also, we want to expand our set of ops that we ship with Hexagon and N. And so TVM fits this bill. TVM lets us do it. And I'll talk about exactly how this works in the case of Hexagon N a little bit later. So here's what we've done so far. So this is a typical flow. I'm not sure if I have a pointer. Wait, how do I go back? Okay, I don't have a pointer here. But okay, so here on the left, so the blue boxes are sort of like functional units within TVM. And there is a script, there's an inference script on the left-hand side, and there is a pathway that goes through the TVM, and then at the end there's an answer. And the cornered boxes, the one with the light blue, are the ones that describe our contributions to it. And so these two slides, this one and the next one, will help you make some sense out of the code that we have written once we upstream it. It's not upstreamed yet, but we're working on it, and hopefully it will be available soon. So pretty much everything starts with the schedule. And we have developed a few schedules that are Hexagon and HVX specific that are meant for a particular set of operations. But more importantly, we made sure that we support all existing and all available directives in schedules. So things like, so many of them actually don't require any work, like reordering or tiling or things like that. That's already happening entirely within TVM. But there are some things that do require support from the backend. For example, in our case, that was prefetch. Also, multi-threading. And in fact, most of what we have in CodeGen went to support those scheduling primitives. So our CodeGen at the moment is fairly basic. There isn't really much more in it than what I just said, and supporting for multi-threading, prefetch, and a few other things. Now, if you want to use TVM as a compiler for ops, that's where the flow would end. It would end at the CodeGen. Now, you can actually run things on Hexagon using TVM. And if you want to cross that execution line, you have to keep in mind that Hexagon is considered a device as opposed to host. So if you want to have anything run on Hexagon, you need to designate a part of your code as a device code. And you do it using the bind, or at least we do it by using bind thread access pipeline directive in the schedule. So once TVM separates the host part from the Hexagon, from the device part, you can then execute something, and with the support, with the runtime that we've provided. And we have two different pathways that we support, two different pathways of execution. The one on the top is the one that goes through a Hexagon simulator. And that's the one that's really very convenient when writing ops, when you do active development, because it allows you to run something on Hexagon, actually using Hexagon code, but without any Hexagon hardware. The one on the bottom is actually running things on an Android device, and there you actually run it in the typical environment where your target application would run. Now, what we find in practice when we talk about runtimes is that there tends to be a little bit of confusion because the word TVM runtime occurs in many different contexts and many different situations. And so this diagram here on the right-hand side of the screen is trying to shed some light on what the picture is. And the thing to keep in mind is that dash line between the host side and the hexagon side. So there is a TVM runtime running on the host side, and that's going to be something running on x86 in case you use simulator, or something running on ARM when you run on Android. But at the same time, there is a hexagon side, and on the hexagon side, there is also a TVM runtime, one that's running with the simulator, and there is one running under faster PC on hardware. And so there are 4 different ways you can compile things, essentially 4 different runtimes. You can, 3 of them are exactly the same code, compiled in 3 different ways. The runtime that runs on the simulator is something that we wrote from scratch. It's a fairly simple implementation of the API calls. Now, this isn't what we've done so far is really just very preliminary. We get to the point where we can run things and we can start to look at performance. It's basically a starting point, but there are a bunch of limitations and restrictions. And the notes here kind of highlight a few of those, a few of such restrictions. So first of all, the complex HVX instructions that I've mentioned at the beginning that are the goal here to accomplish, we haven't done anything about that yet. So if you were to take our code, run it, you wouldn't see any VRMPYs coming out. So, but that's something we definitely plan to do. One other thing to keep in mind is that the simulator, although it will run code that has parallel directive in it, it will not actually run anything in parallel. It will always assume a single execution thread. This isn't really a limitation of the runtime. It's just something that it's kind of like a limitation of the simulator, a feature of the simulator. Now, of course, you know that HVX is a vector engine and has vectors, but you may not necessarily be aware of the fact that the scalar core also has vectors, except those vectors are very short. Those are just register pairs, only 8 bytes long. And but there are vector instructions that operate on those short vectors. And if you want to use, if you have a scalar core without HVX and you want to use those vector instructions, the LLVM doesn't yet automatically generate that kind of code. This is something that we are working on also. But at the moment, if you want to use those instructions, you have to explicitly say vectorize in your schedule. Another thing of note is that we support Hexagon, v62, and later. And v62 is the chip model, the version that came in Snapdragon 835. We support both ADSP and CDSP. Those are different types of Hexagon cores and Hexagon chips that go into SoCs. We've added some extended ways that we can configure the runtime and the code generation through TVM target hexagon. We saw that other targets, ARM in particular, uses that to select the CPU version. We kind of went and added a lot more options that you can configure the simulator, for example, or even pass certain options to the LLVM. Now let's go back a little to this notion of supporting other frameworks. And so here the term ML framework may as well refer to Hexagon NN. So the standard you use, the way that it works is that you write a TVM, you write an op in Python using TVM, you pass it to TVM, and it generates some kind of an object file or a shared library. That then gets included in some kind of an operator library, which is then used by a particular ML framework, Hexagon NN in our case. And it may seem like that's it, and it kind of, like on the high level, it kind of, there is really not much more to it. However, there are challenges because a TVM, an op compiled by TVM has every right to assume that there's going to be a TVM runtime. So if it needs to allocate memory or if it needs to start threads, it will have calls to TVM runtime. But HexagonNN doesn't have TVM runtime, and it's unreasonable to assume that any other framework will have TVM runtime. So there has to be some kind of a layer that translates the calls, that implements the calls that TVM runtime would normally implement into whatever functionality there is in the existing runtime. And Jeff mentioned in his presentation this morning this concept of user-defined operators, and there is between the local runtime and the shim-RT, or a part of the shim-RT, there is this UDO layer. That's the glue code between. It's like a universal glue code that's intended to allow people to merge additional external ops with their own frameworks. So this model of using TVM compiled ops in HexagonNN already exists, and as a matter of fact, the Qualcomm AI research group has prepared a demo that they will present next week at NeurIPS. And so for those of you who attend NeurIPS, I encourage you to go and check it out. You actually see how it works in practice. So there are a few challenges, and on the previous slide I didn't mention this, but there is also a challenge with implementing TVM runtime, or implementing or gluing the TVM runtime code with the existing runtime. The problem that the previous slide mentioned was that the local runtime that comes with the particular framework, like for example HexagonNN, may require more information that's contained in TVM runtime. So there is information that TVM runtime simply doesn't have, but it has to be passed to the existing runtime for it to work. And in case of HexagonNN, this is some kind of a contextual information that the runtime needs to know about the state of things at the time when the op was invoked. And in order to implement that, we actually had to extend TVM to be able to understand parameters to ops that apparently are not used anywhere in the code, but they need to be packaged in such a way that the TVM RT call can unpackage it and pass it to the NN runtime. And so this is here the fourth bullet, the need to add custom attributes kind of goes into that. And the reason why it's a challenge, it's not so much the technical aspect of it, is that this is a vendor-specific extension that we hope we find a way to integrate in the source code with the TVM community. Of course, it will require some discussions, but from my point of view, at least, it was sort of a decision that wasn't taken very lightly, because it's something that you kind of impose for your own needs. You kind of impose some kind of a definition that needs to go into the public repository. But hopefully, we will find a way to do it, and we'll find a way to do it in such a way that future extensions for different vendors can also be incorporated. Going back to technical problems, prefetch turned out to be one of the bigger ones, and the reason is that the prefetch that existed in TVM right now, at least at the time when we looked at it, assumed that you only prefetch a cache line at a time. The prefetch that we have prefetches a block of memory. So you start it ahead of the loop, you put it in front of the loop nest, instead of inserting it in each iteration. So we had to actually change the way that TVM handles prefetch. We had to change the implementation, move things around. We did preserve the existing implementation. We just added to ourselves the option of doing it the other way. Again, something that we will need to consult with the TVM community to see how we can put it all together. The other things are sort of more like bugs and things that are nice to have. There are some parameters in TVM that are hard-coded that we would like to have some more control over. So far, they work for us, but it's not a huge headache, but it would be nice to have them customizable. And routine application of specific lowering passes. So this is something that Vita does already. When you build something for Vita, you say vita.build, and it creates the lowering passes. We have to do it right now by hand. But we do have a certain number of passes that are required. For example, allocation of things like TCM that has to be done in a very special way. So so it adds, like having it done explicitly kind of adds a little bit inconvenience to the user, and we would like to make it easy and hard to forget for people to do it. But otherwise things worked quite smoothly, and we were actually fairly happy with how things, how the whole thing went. In terms of future work, of course, let me start with the upstreaming. Of course, we started this this effort in May this year, so it's been about 6 months. So from the point of view of external observers, it may seem like nothing has been going on, but there has been going on, and we're working on it, and hopefully it will be resolved, and we will be able to publish our code within some reasonable future. Now, other point is that we definitely want to work on CodeGen. We want to be able to generate all these complex instructions that we are so proud of. We want to also be able to build entire graphs. So that's what the real compilation is talking about. Otherwise, we had a very positive experience with TVM. We think that it's a good fit for our needs. We like working with the TVM community, and we hope to increase the degree of our involvement in it. And that's all.
Any questions? One question for you, I guess, is what is the hardest instruction to map right now, like on the DSP?
The hardest would be variants of VRMPY. So VRMPY is this famous instruction that everybody wants to see in their code. It's what it does is it does partial reductions. It does.
Oh yeah, here we can try this one.
It does element-wise. It takes two vectors, or a vector and a scalar, and it does dot product. But it does dot product in a vector of 128 bytes. It would do dot product of 4 elements at a time, and so you end up with four-way multiplication, and then it accumulates that to an int32. Now the problem with this instruction is that it's very helpful and very useful for things like matrix multiplication and convolution. But the problem is that it does only part of that operation. And so if you want to find the opportunity for it in LLVMIR, it's difficult because typically the code is written in such a way that it doesn't expose that particular sub-component of the operation. Now in TVM, we can just generate these instructions based on the analysis of the algorithm. And in order to exploit this, I mean, the way those instructions don't generally exist on their own. They are a part of a bigger scheme, bigger sequences of instructions. And so generating those instructions one at a time doesn't make much sense. What makes sense is implementing algorithms using those instructions. And that's what we hope to accomplish through TVM.
Sweet, cool, thank you. All right, thanks a lot. All right, up next, we're back on the research side. So Zhihao is here from Stanford to talk a little bit about his recent SOSP work on optimizing graphs.
Hi, my name is Zhihao, and I'm a PhD student at Stanford. So today, I would like to talk about our recent work on optimizing deep learning computation with automated generation of graph substitutions. So every deep learning model is described by a computation graph, and each node in the graph denotes some tensor algebra computation, such as convolution or ReLU, and edges indicates data dependencies. And today, in existing machine learning systems, we use rule-based optimizer, which includes a list of manually designed rules. So one such rule could be you can fuse a convolution and the following ReLU into a fused operator. And we can iteratively apply these manually designed rules on an input computation graph in order to obtain an optimized computation graph. And each rule is implemented in source code, and the figure shows the TensorFlow code for fusing convolution with ReLU. And today, TensorFlow involves around 200 different rules implemented in around 53,000 lines of code. And we think there are a few limitations with the existing rule-based approach. First is robustness, because these rules are manually designed based on human heuristics on common models and hardwares. And we found that these heuristics do not necessarily generalize to all models and hardware combinations. And as a result, you can find people on GitHub or Stack Overflow complaining that if I turn on TensorFlow's optimizer, sometimes my performance is slower instead of faster. and they just don't understand why. And the second limitation is scalability, because new operators and new graph structures are introduced in our machine learning framework on a regular basis, and we must be able to support optimizations for these new operators. However, doing this in existing rule-based approach is very expensive. For example, TensorFlow currently involves around 4,000 lines of code to fully optimize convolution. And you can imagine a similar amount of engineering efforts to optimize every single operator added into our machine learning systems. And the third problem is performance, because human heuristics can miss some subtle optimizations for very specific model and hardware combinations. And let me show you one motivating example. So the left figure shows the optimized graph by existing rule-based approach, and that is a ResNet modular, which is a very commonly used one, and people have spent lots of effort trying to optimize that. However, we found that it is possible to further optimize it using some non-trivial transformations. So first, we can change this 1-by-1 convolution to a 3-by-3 convolution by enlarging the kernel. This is possible because you can just set the extra parameters to be 0, so that mathematically you still compute the same thing. But note that this actually decreases your performance because you introduce additional computation into your model, right? And you may wonder why we do that. This is because if you have the convolution with the exact same kernel size, you can fuse them to a single 3-by-3 convolution kernel. And this is an optimization because it reduces your access to input tensor from twice to just one time, and also reduce the number of kernel launches to GPU device. And in addition, you can also fuse addition and previous convolution by changing the weights in the convolution. And finally, you can fuse the convolution and ReLU as before. And we compared the final graph and the original graph on different GPUs and found very interesting results. And the final graph is 30% faster on V100 GPU, but 10% slower on KT GPU, which means that if you are using different GPUs, you might want to do different optimizations. And we found doing deep learning graph level optimizations is very hard because it depends on the operators you are using in the graph architecture, and also the underlying hardware you are trying to run the model on. And different combination of the three components makes it infeasible to manually design optimizations for every single combination of the three components. And so one research question we are trying to address in this work is, how should we address the high complexity of designing deep learning graph optimizations? And our work is called TASO, which is a tensor algebra SuperOptimizer. The idea is very simple. We are trying to replace existing manually designed graph optimization with automated generation and verification of graph substitutions for deep learning. And this will bring two benefits. First, our approach requires significantly less engineering efforts. So for example, today TensorFlow involves around 53,000 lines of code for graph optimizations. And in our implementation, we only require 1.4 thousand lines of code to fully specify these manual optimizations. And second, this also leads to better performance because we can automatically discover novel graph optimizations that are currently missing in existing frameworks. And as a result, we can improve the training and inference performance by up to 2.8 times. And every graph substitution describes mathematical equivalence between two subgraphs. So this slide shows one example substitution. It says that if you do convolution on the same input but different weights, that is equivalent to first concatenating the weights, do the convolution, and finally splitting the outputs. And in order to generate these graph substitutions, TASO takes as input a list of operator specifications that describe the operators supported by the hardware backend, and also the definition of these operators. And using these specifications, we can automatically generate candidate substitutions. And then they are sent to a substitution verifier to formally verify the correctness of this substitution. And finally, we can use this verified substitution to optimize an arbitrary input computation graph. And in order to optimize a computation graph, so TASO includes a search-based graph optimizer that considers how to apply our verified substitution on the input graph. And apply different substitutions will give us different computation graph. And this can form a search space of billions of potential computation graphs that are equivalent to your input graph mathematically, but have very different runtime performance. And we can explore the search space of potential graphs and can generate an optimized computation graph. And there are two key challenges using this approach. First is how to generate these potential substitutions automatically. And second, how you can verify their correctness. And we use two techniques to address the problems, and I will explain them later. And in order to generate substitutions, TASO considers all operators supported by the hardware backend as basic building blocks, and consider how to use these operators to construct different computation graphs. And we enumerate all possible graphs up to a fixed size using these available operators. And in our evaluation, we enumerate graphs with up to 4 operators, and this gives us 66 million different graphs. And because every substitution is mathematical equivalence between two subgraphs, so one naive approach is just directly evaluate all pairs, but this requires a quadratic number of comparison. So we use a fingerprint idea. So we can run all generated subgraphs on the same randomized input. And the output of each computation graph becomes its fingerprints. And fingerprints provide a very nice property, which is if two graphs have different fingerprints, they cannot be equivalent because they generate different outputs on the same input. And as a result, we are only interested in pairs of graphs with identical fingerprint. And each such pair becomes one candidate substitution. And overall, TASO generates around 29,000 different substitutions by enumerating graphs with up to 4 operators. And we also apply a number of pruning techniques to eliminate substitutions that can be captured by more generalized one. And after the pruning techniques, we only need to consider 743 substitutions. And the pruning details are in the paper, so I will skip that. And once we have generated these substitutions, because they are generated using randomized input, we would like to verify that they are correct for arbitrary inputs. And our graph substitution verifier also takes as input a list of operator specifications that describe the mathematical properties of different operators. So one example is that convolution is distributive over concatenation. And another example is that convolution is bilinear to its weights and inputs. And we describe each mathematical property in first-order logic. So for the distributivity of convolution, we say for arbitrary x, W1, W2, if you do convolution over the concatenation of the weights, that is equivalent to distribute the convolution into the concatenation. And that is correct for arbitrary inputs. And in order to verify one substitution, for example, for our running example before, we can ask for a counterexample. Because if this substitution is incorrect, there must exist at least one counterexample that the two graphs give us different outputs. So we ask, does there exist any counterexample? And we can send this query along with all our operator specifications into a theorem prover. And if the theorem prover returns unset, meaning that it can prove there won't exist such a counterexample, then we know this substitution is correct for arbitrary case, and we prove its correctness. And overall, we use 43 operator properties shown on the table. And in terms of the runtime, we can generate 743 substitutions in around 5 minutes. And we can verify their correctness against 43 operator properties in around 10 minutes. And one interesting result is that although these substitutions are generated using randomized input, they are actually all correct and can be verified using our theorem prover. So which means that the fingerprint is very efficient for generating graph-level optimizations for deep learning. And based on our experience, supporting a new operator only requires a few hours of manual work to discover the right mathematical property for the new operator. And again, we require significantly less engineering effort compared to manually specify every single optimizations. And once we have verified these substitutions, we would like to apply them to optimize an input computation graph. And we use a search-based graph optimizer based on our previous work at ICML and SysML. And the idea is to apply, the goal is to apply this verified substitution to obtain an optimized computation graph. And so one key component of our optimizer is a cost model. So instead of running the graph on the actual hardware, the cost model can accurately predict the cost of the computation graph. So the cost model is based on the summation of individual operators' cost, and we can measure the cost of individual operators directly on the hardware backends. And we use cost-based backtracking search algorithm. This will allow us to backtrack local optimal solutions and explore a broader range of different substitutions. And based on our experience, optimizing a model from scratch takes less than 10 minutes. And we think this is acceptable because in order to deploy a model on a hardware, you only have to run this optimization once. And now let me show some performance evaluation. So first, we compared TASO with some rule-based optimizer on V100 GPU using cuDNN library. And later, I will show a result with using TVM backend. So all these TASO and the three baselines all using the NVIDIA cuDNN library. So the performance difference only comes from running different computation graph. And on standard models, such as ResNet, TASO can achieve competitive performance. So this means that TASO is able to automatically generate all performance-critical substitutions for standard models. And the more interesting result is on these new emerging models, for which TASO can achieve a larger speedups. And you may wonder why you can achieve better speedups on these new models. So we have digged into these new models, and we found they include some new operators and new graph structures that hasn't been fully optimized in existing frameworks. And because we can automatically generate these optimizations, we are able to achieve a larger speedup compared to existing baselines. And we also run the experiments using the TVM on the TVM backend. And we run the original graph on TVM and run the optimized graph by TASO on TVM. And again, we can achieve similar speedups on the TVM backend compared to the cuDNN backend. And next, we would like to understand which substitutions are useful to optimize our models. So we do an analysis of used substitutions. And the figure shows the heat map. So every column shows one substitution, and every row shows one model. And the number indicates how many times this substitution is used to optimize that model. And the orange boxes shows substitutions that are currently missing in existing TensorFlow implementation. And one very interesting observation is that it turns out different deep learning models actually use different substitutions, which means that if you have spent lots of effort trying to optimize ResNet and have discovered all these substitutions, this substitution won't help you improve the new models such as BERT and NAS-RN. You really need to see these new models and figure out what are the operators and graph structures in these new models in order to figure out how to optimize it. And so for that, we think TASO is better positioned because we can automatically generate these optimizations. And to conclude, TASO is the first deep learning optimizer that can automatically generate substitutions, and will require less engineering effort, achieve better performance, and also provide formal verification. And TASO has been fully open sourced, and currently we support DNN models in ONNX, TensorFlow, and PyTorch frontend. And we're also considering to integrate TASO into the TVM stack, because the idea is that TASO can be used to automate the graph level optimizations in TVM. And with that, I would be happy to take any questions. Thank you. Yep, go ahead. So he has one question.
Okay.
Oh, thank you for the presentation.
Thank you.
I was wondering, is there any limitation for 4 operators in the graph search?
Oh, so what's the limitation? Why you only use 4, not 5? Because saving the fingerprints. Because if you try to explore larger graphs, there are just more candidates. And currently, just saving the fingerprints of 4 operators requires around 50 gigabytes of memory. And we need to implement a distributed generator in order to support larger graphs. So that's one limitation. Yeah, go ahead.
So quick question for follow-up on that. So when you do the substitution generator, are you just do like brute force permutations of existing operators to generate that the kind of dictionary for the 4 operators that you have, or how do you? What is the summary algorithm for producing that patterns for operators?
Oh, I'm sorry, I got
like
lost.
you have to generate the substitution kind of patterns, right?
Right.
Did you do like a brute force, or just like combining different operators?
Yes.
That's why I think okay.
Yes, yes.
Right.
So because we would like to generate to explore generic optimization that can be applied to
It's a
arbitrary.
huge permutations on the
Right. We just enumerate all permutations of these operators. Yep. Thank you. Yep. Go ahead.
So once the optimization is figured out that these are the operators need to be combined, but what if someone writes a new element-wise operator which is for which the implementation is not written, like optimized implementation. So the graph optimizer would be able to figure out that these need to be combined, but one still has to go inside TensorFlow or other framework to write optimized implementation of those operators.
Oh, so the optimized graph in TASO can be directly used by existing frameworks such as TensorFlow, PyTorch, and if you have a new customized operator, and so in order to use TASO to figure out how to optimize it using this new operator, you need to add it to our operator specification, because first you need to tell us what is the semantic of this operator, what's the definition, and we can automatically generate and verify, what are the potential substitutions that are related to this new operator. So it requires some manual work.
Right. But I was saying that many times performance is also limited by someone introducing a new element-wise operation, which is basically not written as a fused operator in the end in an implemented fashion, optimized implementation fashion. So sometimes that limits the performance. So heuristic implementation is like one's challenge to go, but the next challenge is basically having their optimized implementation inside the frameworks.
Oh, I'm sorry, I don't think if I understand your question, but we can talk offline maybe. Sorry. Thank you.